Okay, so today's lesson, we're going to go through a warm-up first, and we'll talk about what's on the topic, I guess. Just to recap, I guess, again, where we've already learned geometric and arithmetic sequences and series. This warm-up is practicing series. Okay, so finding the sum of a bunch of numbers. Okay, so we have a formula for that, but we also have sigma notation. Okay. So let's look at the first one. It says, what is the sum of the first 12 terms in a geometric series? Now on the test, I'm not going to say geometric or arithmetic. I'm just going to say series. So you're going to have to be able to look at the list of numbers and identify the pattern. I think it's pretty safe to say it's geometric. What are we multiplying by each time? Yeah, -3. Okay, so it's obviously geometric. Okay. All right. Now, if we're finding the sum of a bunch of numbers, there's two ways that I talk about doing this. One way I prefer more than others, and y'all know already that's sigma notation. Right? I like sigma notation. So where you have n equals something, and then a number at the top there, and then something in parentheses. Okay, we'll talk about that in a second. The second way, if you just want to remember a formula, that's fine too. You can do S sub n equals your first term, 1 minus your rate to the n, over 1 minus r. Either formula is fine. I don't like doing this because I don't like remembering another formula. I think this is easier because it's just remembering how to write the explicit formula. Okay. All right, so recap. What goes right here? N equals what? Yeah, if you're ever writing your own list, if you're ever writing your own sigma notation from a list of numbers, it's always going to be n equals 1 because it's your first term you're starting with. What number goes up top? 12 is the last number that you're starting with, or the last number that you're ending with, right? You're going from your first to your 12th number. All right, what goes in the parentheses? Explicit. Always explicit. You're just going to have to decide whether it's arithmetic or geometric. In this case, I tell you it's geometric. So, if anything, try to at least maybe memorize the explicit formulas. A sub 1 times our rate to the n minus 1. Okay, at least remember that. All right, help me out here. What's the explicit formula? 1's our initial value. Our rate is -3 n minus 1. Okay. How do you put that in the calculator? Okay. Yeah, so it has to be, now first of all, how I wrote it here, type it in exactly like that. Remember how you do it in the calculator is go to math. You're going to go over to number 0, and you're going to see it has that little summation symbol there, okay? So pick that. And whenever you get there, you're going to get a blank sigma that has a bunch of spaces to plug stuff in. You're going to have a space for your n. You just put that at x. You have a space for your number here, a space here, and then you have parentheses to plug this in. Okay. What do we get when we did that? 17? Dang it, man. Who's got that? All right, let me right. Negative what? Oh my goodness gracious. All right, we agree on this number right here. Okay. All right. Now, if you did this formula right here, you would have got the same exact answer. So, all right, just either one's fine. Questions on that? Pretty much our lesson from 2 days ago or yesterday. All right. Then number 2 is really just being able to interpret and understand what the sigma notation is saying. It says find the number of terms, the first term, the last term, and then evaluate. So let's start with the number of terms. How many terms do we have in this example? Yeah, 10. We're going from the first term to the 10th term. That's 10 numbers. All right, what's our first term? Exactly. So if I want to know the first term, you plug in that bottom number n for n, right? So that's like having 1 minus 3, -2. Our first term in this pattern is -2. Our last term, if I want to know our last term, what do I plug in? Yeah, you plug in the top number n for n. So that's 10 minus 3, 7. Now, if I wanted to know what the summation of this pattern is, which in this case, that's a linear equation, that's arithmetic, what you get? 25. All right, how do you feel about that? I mean, that's really basically catches up stuff to everything we've done. You got two things that we're talking about today. They both have to do with a geometric pattern. Okay. The first thing, I think this is really pretty cool, is still dealing with sum and series, but we're talking about the sum of an infinite geometric series, an infinite amount of numbers. How can you possibly do that for us? Take a sum of a bunch of numbers. How's that possible? Because it keeps going on forever. Wouldn't that sum just be infinity? No. Let's talk about how. About what? It's pretty cool. Now, this can only happen in a couple cases. This can only happen if you have a geometric series and that your rate is, or the absolute value of your rate is less than 1. Another way of writing that is that your rate is less than 1 and greater than negative 1. As long as you have these two criteria, all right, then you can find the sum of an infinite amount of numbers. Okay, let's think about it this way. Like, okay, for example, let's say I'm on a football field. All right, I'm at one end zone, I'm going to the other end zone. That's 100 yards. Okay. All right, so let's say my rate is 1/2, meaning like I'm going half the distance each time. So, like, if I go half the distance, I'm at the 50-yard line, right? If I go half of that, I'm at the 25-yard. Half of that is 12.5. Half of that is whatever. And I keep going half the distance. If I keep going half the distance, am I going to reach the goal line? No, right? But, you know, it's eventually going to get to a point where I'm so close to the goal line it looks like I'm touching it, right? Because I'm still going half the distance. Even though I'm going half the distance, I know where I'm going to end up, right? I'm going to end up at that goal line eventually. As I go to infinity, I will eventually reach the end there. So even though I'm going an infinite amount of numbers, because they're getting smaller and smaller and smaller, it's okay to assume what the infinite sum would be. Does that make sense? You see what I'm saying? Mm-hmm. And that's why your rate has to be between -1 and 1, because it's a fraction, because it's getting smaller and smaller. I think that's pretty cool. Right. Now, some guy smarter than me figured out the formula here for that. So maybe star that, have that available if you ever need to maybe look at it, maybe highlight it, maybe write it on a list of formulas that might be helpful in a future time. Okay. Wink, wink. Okay. Let's look at an example. Okay. It says to take your first value and divide by 1 minus your rate. You only need to know two things, your first and your rate. So, but the only time you can use that if your rate is between -1 and 1. Okay, so please, if your rate is like 5, don't use this formula and just say does not exist. You can't find an infinite sum. Okay. All right, so let's find the sum of the series. Now, this is how I'm going to do it exactly on your test. Okay, I'm just going to give you a list of numbers, and I'm not telling you it's infinite. This ... right here, that means that it's infinite. If you've got ... that just means it's going on forever. Okay. Now, if it's going on forever, then there's only one way you can find that sum, and it's if your rate is between -1 and 1. If it's not, what are you going to say? It does not exist. Because if your rate's not that means the numbers are getting infinitely bigger, and you can't find the sum. Okay? So that's the first thing you got to do. You got to identify what your rate is. Okay? You got to make sure your rate's between -1 and 1. Good. All right. Some people might not be able to see that just by looking at it. So if you can't, just remember, take one term and divide by your previous term. And that ends up being -1/7. Is -1/7 between -1 and 1? Yes, it is. Okay, so I'm able to find that infinite sum. All you have to do, and some people denote it this way, is do your first value, which is 21. Divided by 1 minus your rate, which was -1/7. And that's kind of, I mean, I would type it in the calculator exactly like you wrote it there. Let's see what we get. Yeah. I mean, do your fraction symbol, do your point. Yeah. If you didn't get that, talk to me. We'll figure out why. But I'm saying the infinite sum is 18.375. I think that's pretty cool because look at the first two numbers. 21 minus 3 is 18. So I'm saying every number in the pattern to infinity from that point is just going to equal 0.375. That's pretty cool. What your minds yet? No? Questions on that? Let's try, not that example. Let's just try this one. This one? Actually, I like this one. Let's do this one.
Yeah.
Well, because you can see the pattern here. The rate here is what? Yeah, one half. We're doing a half each time. Okay. What's the rate down here? Yeah, we're dividing by 3, which is the same thing as multiplying by a third. So those rates, I think, are easy to see, and those would both work. Here, you might not be able to see the rate as easy in this example over here at the top right. So think about that one. Sure. You got negative 3/4? How'd you get that? Yeah, absolutely. I mean, it might be hard to see with these fractions. So remember how we can always figure out the rate is take any term and divide by the previous one. So like you can do negative 9/4 divided by 3. Do that in the calculator. Just do it in your by hand. You end up getting negative 3/4. Okay. So you can always figure out the rates. Always make sure. So negative 3/4 is that between negative 1 and 1? Yes. So we can find the infinite sum. All right, so that would be our first value, 3, divided by 1 minus my rate. I'll let you type that in. Do we agree?
Yes.
1.7?
1/4.
Okay, rounded, whatever. You give me the decimal, you give me the fraction, I'm cool with that. Everybody get 1.74, I'll make sure all agree on that. Alright, questions on infinite geometric sum. Alright, okay, so we talked about infinite geometric series. There's another application I want to talk about, geometric, and this is something you've seen in the past, so hopefully you can remember it, okay? Exponential growth and decay. Who remembers seeing that stuff in the past? Yeah, I know you have. Yeah, I mean, think about the explicit formula for geometric, right? It was a sub n equals our first term times our rate to the n minus 1. Well, that's just, we talked about this in the previous lesson, that's just an exponential equation, right? So an exponential equation is good with showing growth and decay over a certain amount of time. Who's seen it as a times b to the x before? Yeah, exactly. Okay. Where a is still our initial value. Okay. B is not going to be our rate, but it's going to be our growth or decay factor. It depends on the problem whether it's growth or decay. And that's found using your rate. Okay, it's found by doing 1 plus or minus our rate. Okay, we just have to decide whether it's growth or decay. If it's growth, we add our rate. If it's decay, we subtract it. And then x is just going to represent our amount of time. So just how much time's passed. So another way you might see this written is a times 1 plus or minus our rate to the x. Okay? Because we got to find our u. Let's, I'm probably going to skip around some of these examples. Let's just kind of see what we got. Oh, sorry. Everybody good? All right. Here's a good example. We buy a car for $20,000. Okay? As soon as you take that new car off the lot, instantaneously it depreciates. Okay? It goes down. That's what happens with cars. And in this case, the annual rate of decrease is about 15%. So your percent is going to be your rate. Okay, this right here is your rate. How much you're going down by. It says find the decay factor for the car. It's asking for the factor. It's asking for your B value, okay, which is not your rate. Your rate tells you how much you're decreasing by. Your decay factor tells you what percentage of the car you have, or the value of the car that you have after a certain amount of time. Okay. So since this is decreasing, we find that by doing 1 minus our rate, or 1 minus 0.15. Just a point. So basically that's 85%. What I'm saying is that after a year, since we're talking about annual, after a year, we have 85% of the value of the car. It decreases by 15%, I'm left with 85% of the value. You see the difference? All right, so we have B, and then the next question says, suppose the rate of decrease continues to be 15%, write a function to model the value. Okay? So if we ever need a function, all we need to know is what A is equal, what B is. And we're good. All right, we know B, we just found that, it's 0.85. What's our A value? Yep. $20,000 is what we started with. If we have those two numbers, we have our formula, right? So that is, it's in terms of y and x, so y equals $20,000 times 0.85 x. What that's saying is that you're starting off with 20,000 and you're doing 0.85 of that every year, however many years it is. Just going down 15%. All right, find the value of the car after 10 years. What do? Kevin? Plug in 10 for x. X represents time, right? So that's just 20,000 times 0.85 and 10. I don't know. 39 something.
37.
That makes sense to me. I mean, a 10-year-old car going from 20,000 down to about 4,000 is about right. I got a 2008, I got 2009, and I bought it for about that much. Makes sense. Questions on that one? All right, we're skipping an example. Let's go into this one. But on my notes online, they're all filled out, in case you're curious and you don't want to go back and look at the notes if you need another example filled out. Okay, it says a collection of 20 Star Wars figures were bought in 1978 for $250 each. Seeing as these figures were kept in their original packaging, the value of the figures have increased by 4.5% per year since they were bought. Let's write a formula to model the value of the entire collection. So remember, if we need any formula, we just need an A and a B value. So we have our formula. All right, how do I find my A?
20 times 2 plus 5.
Right, it's my initial value. Don't tell me it's just 250, right? Because there's 20 of them. So my entire collection is worth $50. For B value.
1 plus 4.5.
Good. It's increasing, right? My B value is going to be then 1 plus whatever my rate is. Okay? Well, my rate in this case is 4.5%. Please make that a decimal. 0.045. So that's 1 plus 0.045 or 1.045. I got my A, I got my B, I got my function. Y equals my initial times my growth factor to the x. What will the collection collection be worth in the year 1999?
Gotta get our stuff.
What is it? Let's see. What value do I plug in for X? 21, right? We started off in 1978. The amount of years that have passed were 20. Oh my God. 21. So if I wonder how much they've increased by, it's going to be 50 times 1.045 to the 21st power. I think it's like $100 and something dollars. 126. I mean, what? After 21 years, it's gone up by like what? $76. Does that make sense, though? Cool, okay about it? What about this next piece of it? It says that after 1999 and the release of episode 1, for whatever reason, that makes this value starts to depreciate, starts to decrease, and now decrease at a rate of 2.3%. Well, I don't want to know how much the collection is worth in 2012. Can I use the same formula I came with up here? Oh, it's not growth anymore, it's decay. We haven't changed up. Who thinks they have the equation? OJ? Yeah, so we're starting at 99 is when it started to depreciate. So I needed my initial value at 99, which I figured it out right here in the previous problem. So 126.01, 0.977. Tell me how you got that. Good. Right, so this is decay, it's 1 minus our rate. That's how we got that. And then raised to what power? Yeah, 13, because the difference between 2012 and 99 is, what'd you get? I think it's like 90 something.
93.
Point. That's still not, not down to 50, so you're good. You're still taking a problem. How do you feel about these types of problems? Feel okay? All right. I got. Okay, this problem right here. This shows up sometimes, and it's not supposed to be hard. It's just to help you understand, to be able to read and interpret these things. Okay. It says tell whether each function represents exponential growth or decay, and then state the rate of growth or decay. So it's asking to identify what type of equation we have, and then find that R value. So let's look at A. 5 times 3 to the x power. Growth, right? Growth. Just a recap, I don't know if I really wrote this down, but it's growth when our R value, when our R value is greater than what? 1. And it's going to be decay when we're dealing with these types of problems. I know with exponential explicit, you can have a negative rate, but with these types of problems, if our rate is greater than 0 or less than 1, it can never be negative. If it's a fraction, then it's decay. So it's growth here because we're greater than 1. How do I figure out what my rate is? Good. Think about how we got that value. It was 1 plus our rate equals 3. So you subtract 1 and we get 2. All right, what about the next one? It's the growth or decay. Decay is a fraction. Good. All right, 1/3 is a fraction. That's less than 1. It's decay. How do I figure out what my rate is? Yeah, well, close. Well, 1, yes. Think about how you set it up. 1 minus your rate equals 1/3. So just work backwards and maybe add R and subtract 1/3. What's 1 minus 1/3? 2/3? Steve's a fraction, so is that growth or decay? It's growth. I try to trick it. It's a fraction greater than 1. Okay, because it's greater than 1, that makes it growth. Okay, that makes it growth. All right, so that means that I would do 1 plus r to get 5/3. And that means r has to then be what? What's 5/3 minus 1? 2/3? Does it make sense? You think you can identify that? Y'all been killing it today. I got one more thing I want to talk about just because it's important. Not that. This, not that. This, yay. Yeah, unfortunately you gotta know it. Half-life is seriously the same exact equation as our exponential growth and decay problem. It's just that it's going to be a special type of decay. Okay? And it's a decay where we manipulate the b value and we force it to be 1/2. So it's going to be y equals a times 1/2. And the reason we make it 1/2 is because we also manipulate the time. We make the time, instead of just x, we divide that by our half-lives, whatever the half-life is. And that kind of manipulates the problem for us. Okay? So again, star it, circle it, square it. Who's seen half-lives before, like science? Alright. And really the half-life is, it just tells you the amount of time that it takes for an element or whatever to reach half of its original amount. Okay? And that's useful in like carbon dating and stuff like that. Like what's carbon's half-life? I don't even know what it is, but they use it. You're right. Your mom's a science teacher. You're supposed to know that. That's true. Pretty much. Listen, I'm not a Math 1 teacher, but I know Math 1. See, I'm not a statistics teacher, but I know statistics. Oh. Ooh. That's not true. I don't know statistics.
Liar.
Okay, I do know.
Who else lives in your house?
What? Let's keep going. They're not even watching this video, to be honest. They probably quit at minute like 15 or something. They do watch it, really? Oh, yeah.
They probably skip through it.
Yeah, just give it through. They're listening to our conversation right now, I'm sure.
No, they probably skipping.
Hey, how's it going? What if is it going all right? I'm sure it's boring. I feel bad for them, but that's what we got. Love you guys. Okay. All right. Half-life. Yeah, half-life. So just know that formula. Let's plug some stuff in. So the potassium has a half-life of 5 years. It takes 5 years for it to reach half of its original amount. That's how long it takes for it to decay. If you start with 250 milligram sample, how much will you have for 12 years? Okay, well, because we know the half-life, we can force our rate to be 1/2. It's like we're like given a known rate. Okay, so we'll say y equals. We need to know what A is. What's A? 250. We're starting off with 250 milligrams. We're forcing our decay factor to be 1/2. And 12 is the number of years, but I want to divide and put it in terms of half-lives. 12 divided by 5. I don't know, that equals something. It's going to be less than 250 because we're decaying, right? 2 point, what? 47.37 milligrams, good. What about working backwards like we've done so many times with the measure explicit? Yes, carbon has a half-life of 3 years. How much carbon would you start with? So it wants to know what A equals if after 9 years you have 30 milligrams left. Good. So 30 is going to equal now, because that's what we're given the end game. We're working backwards to solve for A. 1/2. The amount of years that it passes is 9, and our half-lives are 3. So what's that? 30 equals A times, is that 1/8? And then divide both sides by 1/8.
Yeah.
So, is it 240? What do y'all think? Alright, I realize I've given you like a crap ton of formulas and stuff, but hey, just keep them highlighted and written down and something might happen, I don't know. Okay? Thanks for listening, hope you understand it. Okay, bye.